Welcome back to The Survival Historian. Today, we're exploring a mystery that has stood for nearly 2 millennia, not as a ruin, but as an undeniable monument to human ingenuity. Imagine for a moment a material so resilient it actually grows stronger with age, while our modern concrete, well, it just crumbles to dust. The year is 27 BCE. Roman engineers pour concrete into ocean waters, building monuments that will outlast empires. Meanwhile, in our world, billion-dollar infrastructure fails within just a few decades. What did they know that we somehow forgot? Today we uncover the lost superpower of ancient Rome. Consider the facts. The Pantheon's massive concrete dome still stands as the largest unreinforced concrete structure ever built. Roman port structures at Caesarea, submerged in seawater for 2,000 years, remain structurally sound. The San Francisco-Oakland Bay Bridge, completed in 1936, required a seismic retrofit barely 80 years later. Concrete highways across America are fracturing. This is not coincidence, it's a fundamental difference in material itself. For centuries, scholars dismissed Roman concrete as a fortunate accident, merely stone and sand mixed with determination. Yet the persistence of these structures demanded deeper explanation. Why doesn't the Pantheon collapse under its own weight? Why do underwater Roman structures not degrade, but instead strengthen in environments that should corrode them? The answer lies in understanding the profound chemical alchemy ancient engineers created, a process so sophisticated that it took 21st century science to finally comprehend what they knew intuitively. This is the story of a lost superpower, structures that heal themselves, grow stronger with time, and, honestly, defy the laws of material degradation. Beneath the Bay of Naples, in volcanic soils surrounding Pozzuoli, lies the foundation of an engineering revolution. The Romans discovered pozzolana, volcanic dust so chemically reactive that when combined with lime and seawater, it created something extraordinary, a material that responds to its environment and repairs itself. The formula seems simple: lime, volcanic ash, seawater, and stone aggregates. But the Romans employed a technique called hot mixing. Rather than using slaked lime already cooled, they worked with quicklime, calcium oxide in its raw reactive form. When water met quicklime, an exothermic reaction erupted, releasing tremendous heat and creating a thermal environment within the mortar itself. This violent reaction fundamentally transformed the material. Within this hot-mixed concrete appeared distinctive white mineral formations called lime-clasts, which early researchers considered flaws. They were wrong. These lime-clasts are the superpower itself. Embedded like tiny time-release capsules, they wait. When a crack forms and water seeps inward, the lime-clasts dissolve, releasing a calcium-rich solution. This solution reacts with atmospheric carbon dioxide and minerals from the volcanic ash, crystallizing into calcium carbonate and strengthening compounds. The crack doesn't just seal, it fills with new, harder material. The concrete actively heals itself. This mechanism reaches its full potential in seawater. As Roman concrete ages in the ocean, rare, interlocking minerals form within its structure. Compounds like aluminous tobermarite and philipsite that reinforce the material at a microscopic level. Where modern concrete degrades in salt water, Roman concrete grows stronger. It's as though the ocean itself feeds the structure, layer by layer, making it more resilient with every passing year. The Romans didn't stumble upon this material. They were master engineers who understood intuitively principles of chemistry that wouldn't be formally codified until the 20th century. Consider the Pantheon's dome. It's not merely thick concrete. It's carefully calculated architecture that grows progressively lighter toward its apex. At the base, dense aggregates bear crushing weight. Toward the top, Romans incorporated pumice stone, volcanic rock so light it floats. This wasn't decorative, it was structural genius, managing load distribution and stress concentration, allowing the dome to rise to impossible heights. The Pantheon's concrete formula changed with each layer, each section optimized for specific function. Romans understood, through observation, that different environments demanded different material responses. Harbour structures received aggregates specifically suited to maximize self-healing reactions in salt water. Inland structures received different formulations. This was sophisticated materials engineering without modern testing equipment. Examine the harbour structures at Caesarea Maritima, built with Roman expertise. Massive blocks of Roman concrete were dumped directly into the Mediterranean. For 2,000 years, submerged and bombarded by waves, exposed to salt that should have destroyed them, they've remained. The concrete has incorporated marine minerals, creating a composite so durable that modern salvage teams find it harder to extract these blocks than to leave them. Romans built not just for their generation, but understanding that time and elements would make their structures more formidable. In the year 1824, Portland cement was invented and patented. For a while, engineers genuinely believed they had improved upon ancient techniques. The modern formula promised consistency, predictability, and, well, controlled setting times. Within just a century, Portland cement had almost completely displaced traditional lime-based mortars. We traded away self-healing properties for speed and uniformity. The consequences of that choice have become apparent only recently. In the 2020s, as researchers, including scientists at MIT, began studying ancient Roman structures with modern analytical tools, they discovered something quite humbling. Concrete from structures built 2,000 years ago possessed properties that actually exceed anything our modern formulations can achieve. In 2023, a landmark study confirmed that the self-healing mechanism was engineered, not just a happy accident. The lime clasts, it turns out, were the essential component of an active, adaptive material system. Modern researchers have now started experimenting with adding these elements back into contemporary concrete. Early results are promising, but also, well, a bit sobering. We simply cannot recreate what the Romans achieved because modern Portland cement behaves fundamentally differently. Yet, the implications go beyond just durability. Roman concrete production required less energy than modern Portland cement manufacturing. As climate concerns mount and infrastructure budgets strain under the weight of repair costs, ancient Roman engineering presents not merely a historical curiosity, but perhaps a genuine pathway forward. You know, the lost superpower of Roman concrete is not really about a single component. It's actually a philosophy, one that acknowledges time as an ally rather than an enemy. It's about understanding that, well, structures should grow stronger as they age, that materials ought to adapt to their environment, and that time should enhance rather than degrade what we build. We stand at a crossroads. Our infrastructure fails not because we lack resources, but because we inherited a material system optimized for rapid deployment rather than enduring strength. The Pantheon remains eloquent argument, an unreinforced concrete dome surviving earthquakes, warfare, neglect, and 2 millennia of weather. It whispers across time that ancient techniques understood through modern science might offer solutions to problems we created through the pursuit of novelty. The survival lesson is this: sometimes tools necessary for our future lie buried in our past. Romans measured success not by quarterly reports, but by millennia. In an age of short-term thinking, there's profound humility in a civilization that built to last 1,000 years. As we face resource constraints and environmental pressures, the question becomes, are we wise enough to look backward, to learn from those who built, to endure, and to reimagine our future through the recovery of forgotten wisdom. The next time you see deteriorating concrete, think of the Roman engineer who mixed quicklime and volcanic ash, understanding somehow that the resulting material would grow stronger with age. The survival lesson is philosophical. True resilience isn't built in a moment. It's built into materials and systems that improve through challenge, that gain strength from their trials. Thank you for joining The Survival Historian. If this journey into ancient engineering resonated with you, please like and subscribe. The wisdom of the past is waiting to teach us how to build a more resilient future.